Okay, so last class we have started electrostatics. Okay, so today we will continue the same topic. I think last class we discussed about the basic introduction of this chapter, and we also started about the properties of charge, right? So we have discussed about charge and we have discussed about the methods of charging, right? If you see, we have discussed certain topics, right? So, Chitresh, you remember how much we have discussed last class? Charging methods of charging we have discussed, right? Okay. So, charging by friction, charging by conduction, charging by induction. Up to that we have discussed. Okay. So, let us discuss now some properties of charges. Properties of charges. Properties of charge. And before we discuss this property of charge, we should know what is a charge. What is charge? Before you start with property, so first thing is that what is a charge? What is a charge? The charge is what? Charge is nothing but the property of material, not all material, but certain particles. Like for example, electrons and protons, they have this property called charge. Just like every particle has a property called mass, similarly some particles have this property called charge. Okay, and due to this property there will be certain behavior or certain phenomena will happen. So this is a fundamental property of certain particles. It is fundamental property fundamental property of certain subatomic particles subatomic particles subatomic particles like electron and proton. They are subatomic particles, but neutron is also subatomic particle, but it does not have charge. That means it is not that charge is for every particle does not have charge. That's why certain particles in nature this property is there. Okay. Why? Now you cannot ask question why it is there in nature. It is by some design, already it is available in nature. Whoever has made this nature, he has kept it. You can say God has made this nature, so God has kept it. You cannot ask question why it is there. Okay, maybe due to some reason it may be there, because it may be helping in many other phenomena. So it is related to that, but it has charge, right? So certain particles have charge. This is the property, and due to that charge it has certain behavior. What are those behaviors? Okay, so due to charge, it will show certain behaviors. So due to this property, property, these particles can show electric electric and magnetic behavior behavior or effects. Okay, electric and magnetic effect it will show due to this property charge. Okay, and in nature we know electrons. So one electron, if you consider one electron has a negative charge of 1.6 into 10 to the power minus 19 coulomb. Coulomb is the unit of charge. Okay. Similarly, proton has that much only, but it is positive. One proton has a positive charge of 1.6 into 10 to the power minus 19 coulomb. Okay, so proton has same amount of positive charge and electron also have same amount of negative charge, but they are opposite. One is positive, one is negative. Now why is negative positive? Because again it is in nature. In nature, and also note that this negative positive sign has been fixed by us. It is not that electron has to be negative. Electron you can assume as positive, then proton you have to assume as negative, because by convention we are choosing one as plus, another as minus. Okay, it is pure convention, and based on that convention everywhere all the books have been published. But it is not that it has to be negative. That is our we have fixed that. Okay, we have fixed it like that, but they have different opposite behavior. Okay, then also now the question is, can there be any charge which can be smaller than electronic charge in nature? In nature, can there be any charge which can be smaller than that? Is it possible? What is that? Yes. Can there be any charge which can be smaller than this? Yes. So this you have to note. Quarks. Quarks have charges, and this value you can take as E. Okay, this value you can write as E. E means 1.6 into 10 power minus 19. Now quarks have charges 2 by 3e plus 2 by 3e or minus 1 by 3e, like that. Quarks have charges like 2/3 or 1/3 of that charges. Okay, but the thing is that quarks are unstable. Quarks are unstable. Okay, so in nature they are not stable. That is why we do not talk about that quarks, because even if you break electron can break into in a small subatomic particle. That means further smaller than electron we can have quarks. And there are many things which you will be studying in higher academics. Okay, right now you don't have to worry about this, but there exist some charges which are lesser than electron, but they are not stable. So in nature the only most fundamental smallest charge available and unstable is electronic charge. Okay, electronic charge is the most stable. Okay, then let us understand the, also note the units of charge. SI units. SI unit of charge is coulomb. We already know that 1 coulomb, but there is CGS unit also. CGS unit of charge is 1 ESU, which is called electrostatic unit. Electrostatic unit. And this ESU is a smaller unit, and what is the value of that? The value of 1 coulomb is nearly 3 into 10 to the power 9 ESU. Okay, ESU. So generally we are using these units in physics. If they give in CGS unit, that also you should know, right? This is all about the charges. Now let us go into the behavior or the properties of charges. Properties of charges. First property is polarity of a charge. A charge has polarity, means it has two types of nature. One is positive nature, another is negative nature. So one is plus and another is minus. These are called polarities. Okay, but mass does not have two nature. Mass is always positive, mass cannot be negative. So this property of charge is different than mass. Okay, second thing is additive property. So you can add charges, like numbers. Okay, charges can be added. Charges can be added algebraically. Algebraically. We can add charges like number with proper sign. Okay, for example, there is a charge of Q1 as plus 2 microcoulomb and another charge is minus 2 microcoulomb. If you take the total charge, net charge, it will be Q1 plus Q2, which will be plus 2 minus 2 microcoulomb, but it will become 0. Okay, charges will be added like numbers. So note that charges are scalar quantity, they are not vectors. Charges are scalar quantities. Charges are scalar. Okay, they are not vector, although they have sign plus minus, but that sign plus minus indicates its polarity. It is not indicating the direction like plus minus in one dimension. That one dimension plus minus for velocity displacement, that is direction, because they are vector quantities. But it is scalar quantity and plus minus indicates its polarity. Okay, these are two properties. Let us move to the next property. Property number 3. Property number 3. Third property. So in the third property, we can say charges are they follow the law of conservation. Okay, uh, conservation of charges. Conservation of charges. Conservation of charges. So in conservation of charges, we can say that in an isolated system, system, in an isolated system, total charge remains constant or remains conserved. Total charge of a system, just like a total energy of an isolated system, remains constant, that is conservation of energy. Total mass of an isolated system remains constant, that is conservation of mass. Similarly, this is a fundamental conservation principle in physics. Okay, total charge isolated means you cannot add from outside or you cannot subtract it. Okay, that is what is isolated system. So we can understand this with one simple example which is given in NCERT. In NCERT, there is a very important uh, uh, example is given that sometimes in nature it has been found that a neutron breaks into smaller particles, or it breaks into electron and proton, and there is also antineutrino emitted. Okay, so a neutron breaks into electron and also proton, and there is another antineutrino. Right now you don't have to know more about antineutrino, you have to learn about charge conservation. So neutron is what? Neutron is neutral, there is no charge, neutral, total charge is 0. So this is the system, isolated system. Now neutron has broken into electron proton, so electron has a charge of minus c and proton has a charge of plus c. So still the total charge is still 0, because minus c plus c gives 0. This does not have any charge, antineutrino. Okay, so the total charge is still 0. So you can see, even though nature creates charge but not charges, it is creating charges, electron and proton, and it is creating such a manner that both the charges cancel out and still the total charge is 0. Okay, so this example is given, but this you will be studying in nuclear physics. Last, in modern physics you will be studying afterwards. Okay, but you should know, just for example they have given. But and there are many other examples also, like we have discussed that due to friction, you are rubbing, and due to that some charges are developed. So some number of electron get transferred from one body to another body. Let us say 10 electron get transferred from one body to another body. So the body which lost 10 electron, that will get plus 10 E, and the bodies which get 10 electron, it will get a charge of minus 10 E. So initially both the bodies were neutral. Total charge of the system is 0. Now even after that, total charge is 0. Why? Individual body has got charge, but the total charge of both the body is zero. Clear? So that concept is there. Conservation of charges. It's an important principle. Okay. Then what else? Next, let us move to the next. Property number 4. Property number 4. Quantization of charge. Quantization of charge. The quantization means what? The charge of a body, charge of a body is integral multiple of electronic charge. Electronic charge, integral multiple of electronic charge. So suppose there is a body, right, and this body, the charge is, let us say, q is the charge. So this charge will be n times electronic charge, n times, okay, where n is an integer, n is integer. Integer can be plus minus 1, plus minus 2, plus minus 3, plus minus 100, plus minus billion, plus minus billion, anything can be there, but integer it has to be. Now why it has to be integer? Let us understand that because the body has a charge because of electrons, excess electron or deficiency of electrons. Why excess electron? Because it is able to gain electrons. Why deficiency of electron? Because it can lose electron, because atom as a whole is neutral. So if your body loses electron, then it will develop positive charge. If your body gains electron, it will develop negative charge. So plus minus is because of loss or gain, but it can lose or gain only 1 electron, 2 electron, 3 electron, like that. We cannot gain or lose half electron. So that is why the charge developed will be n times of electronic charge, okay, n times of electronic charge. So it can either lose 1 or 2 or 3 or gain 1 or 2 or 3 electrons, like that. So that is why the charge will be n times c. Now there is a question which is generally asked, that how many electrons, how many electrons are present in 1 coulomb, let us say minus 1 coulomb charge. You know the answer? Yes, you must have gone through it. Yes. How many electrons are there in minus 1 coulomb charge? Yes, any answer? Yes. One, no, 1 electron charge, you already know that, right? Already you know it's a very small, 1.6 into 10 power minus 19. But we are talking about 1 coulomb. Tell me, think about it. If it has not been discussed in your class, then that means this is very basic thing, and everywhere this type of question is coming. Okay, 1 coulomb charge has how many electrons? Yes. Yes, you can substitute here and calculate. That's all. Q you put 1 and E you put electronic charge and calculate the number. That's all. Right? So substitute. Q is 1. Magnitude wise I will put 1. N is the number, is electronic charge, 1.6 into 10 power minus 19. Now you calculate. Calculate this, you will get N as 1 by 1.6 into 10 power minus 19, which will come as 6.25 into 10 to the power 18 electrons. Okay, or even you can say protons, because they have same charge. So this many electrons will give minus 1 coulomb, or this many proton will give plus 1 coulomb. Are you clear about this? Yes. Okay, then let us move to the next. This property is over. Now here there is important point to note. In NCERT they have mentioned repeatedly very important point, that this principle of quantization, principle of quantization, can be ignored, can be ignored can be ignored at macroscopic level, macroscopic level, macroscope. What is macroscopic level? Macroscopic level means a bigger picture you are taking, where you are dealing with 1 coulomb, 2 coulomb, like that. So in front of 1 coulomb or 2 coulomb, charge of 1 electron is nothing, because charge of 1 electron is of the order of 10 power minus 19, which is almost negligible. Suppose if a body has 1 coulomb charge and 1 electron is lost from that body, let us say that body lost 1 electron, so how much difference will make? It is not going to make any difference at all, right? Because charge of 1 electron is so small that it will not make any difference in 1 coulomb charge. It is like that if a person has billions of rupees, then 1 rupee, if he loses, it will not make any difference, right? So that is what it is. They are saying in this CRT, that at macroscopic level, it does not make any difference. Quantization does not make any difference. But at microscopic level, when you are taking, like for example, if you are considering the chemical bond formation, where 1 electron is lost or 1 electron is gained or 1 electron is shared, there each single electron makes a difference. So at microscopic level, we cannot ignore the quantization principle. Are you clear about this? Yes. Okay. So at macroscopic level, you can ignore it, but microscopic level, and why are you able to ignore it? The simple reason is that because charge of electron, because charge of an electron, charge of an electron is very, very, very less, very less it is. So it will not make much difference if you transfer 2 electron, or even if you transfer billion of electron, it will not make difference, because billion of electron means 10 to the power 6. So even 10 power minus 19 you multiply with 10 power 6, that is still 10 to the power minus 13, correct? 10 to the power minus 13 coulomb also doesn't mean anything, it is so small. Okay, so that is why you can ignore this principle at microscopic level, macroscopic level. Okay, right, then let us go to the next is, now whatever I am going to write in the board, that is not given in NCERT. That is my own interpretation by reading the book. You need to read it and interpret it, because in the book everything will not be given very clearly. Okay, NCERT is a book which have been just written, but things are not very clear. That is why in the exam, when they ask questions, we cannot be sure what question there are. Sometimes there is direct, sometimes it is indirect questions, which is difficult to understand. So let us take one important property. So we have so far discussed how many property? 4 property. Next property, let us write some extra properties. Property number 5. Property of cancellation. Property of cancellation. Cancellation of electric effects. Electric and even magnetic effect. But let us write here electric effect. Okay, so what is this here? I will explain this for two cases. One is for um, equal and opposite, equal and opposite charges, and another is for for equal charges, or you can say same charges. Suppose if you take two charges which are exactly same but their signs are opposite, like for example electron or proton. Okay, take two charges. These two charges, if they combine together, that means if these two charges are present at the same point, then they will cancel out all the effect of electric behavior that can happen due to a single charge. Suppose for example there is a charge of plus 2 coulomb. This plus 2 coulomb will create some field and it will create some forces on any other charges. So this plus 2 coulomb, if it is present at a point, it will have some electric effect. Similarly, if you keep minus 2 coulomb separately, it will have its own electric effect. But suppose these two charges are present at the same location, plus 2 and minus 2, these two charges are present at the same point. Okay, present at the same point, present at the same point. Then because they are present at the same point, the sum of the total charge is 0, right? Because plus 2 and minus 2 are present at the same point. If they are present at two different points, then the effect will be there, it will not be cancelled. Okay, but because these two opposite charges and equal magnitude are present at the same point, the whole effect is getting cancelled out. Okay, present at the same point, this effect, no electrical effect, no electrical effect. It will not produce any electrical effect because the resultant charge is going to be 0. Net charge, net charge is going to be 0. This is the concept of equal and opposite charge. But let us say equal charge or same charge, not opposite, same charge there. Let us consider that there is a plus q. Let us write as q in general, q and q. These two charges are present here, here. Now they are not, they should not be present at the same place to cancel out the effect. They can be present at different points. Okay, so let us say two charges of same value, same sign are present at two different places. Now if you join these 2 points, if you join these 2 points, then if you consider the middle point of this midpoint, suppose this is A and this is B and this O is the midpoint of this, then at the midpoint all the effect will be neutralized or cancelled out. Okay, so that means if you keep any charge at this point O, net force will be 0. At this point O, net field will be 0. At this point O, so these two things will be definitely 0. Other things we cannot guarantee, other things will be 0 or not, but these two things, the effect of net force here is 0 and the field is 0. Field is also, we'll discuss field afterward, but force and field, they are going to be 0 at these two, at this point, which is the symmetric point, which is the midpoint of this AP. Are you clear about this? Now we will extend this concept more because this concept is a very good concept and some questions are solved without doing anything. Okay, if you know this concept, because in NCERT they have not explained, but there is just one word they have given, cancellation. But that cancellation is not 100% clear in what context it is saying. But this is the context, how things are getting cancelled, how the effect is getting cancelled, but sometimes effect will not get cancelled. Okay, suppose if you take any other points other than the midpoint, there will be electric field and magnetic field, sorry, electric field and there will be some electric force there if you keep any charge. Okay, so this is the only point where the effect is getting cancelled. This is the most symmetric point. Now let us take some other examples. So let us say there are three equal charges and they are kept in a symmetric manner in a equilateral triangle. Okay, consider like this. There are three charges which are kept on equilateral triangle. like this. You can join these sides, and let us say this side is AAA, equilateral triangle. Now, what is the most symmetric point of this equilateral triangle? Can you guess? Centroid, right? Centroid. So, centroid, if you take centroid, let us take centroid as O. So, at this centroid, if you keep any charge, it will experience zero force, and there is no field here. So that means what? This is the point where all the effects are getting cancelled. Okay, this is the point. So here the force will be zero, force will be zero, field will be there. Other things may be there, like potential may be there, and other things may be there. But the vector, particularly the vector effect means the quantity which is a vector quantity due to the charges. So due to charges, force is generated. Due to charges, fields are generated. They are vector quantities. So vector effect will get cancelled here at this point. Okay. Similarly, now you can you can extend this idea. Let us say there is a regular polygon of n sides, okay, and you are keeping charges on all the corners. Then at the center of that polygon, the net force or net electric field will be zero. Okay, this concept. Now, due to this concept, there is a very nice question is framed. I will explain that question. Okay, let us try. What? Yeah. Gravitation also similar effects are there, right? Correct. Now suppose take a question that there is a polygon. Let us say the polygon has 10 sides. I am drawing only some sides starting with, let us say, 1, 2, 3, 4, 5, like this. This is the n sides and this will be n minus 1 sides. It's a regular polygon, right? So you can join these sides also, like these sides will be there. Okay, so many sides will be there. I am not connecting on because there will be dot, so many sides can be there. Now let us say that on each of these vertex we have a charge, equal charge of q, 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 q. Everywhere you are keeping, right? Everywhere you are keeping, but you are not keeping on the last vertex, which is the nth vertex, or here. Here charge is missing. Let us say you are not keeping any charge here. Okay, you are not keeping any charge here except this point, except one corner. You are keeping everywhere charges. Now the question is that let us say at the center, which is O, at the center, what will be the force if I keep a capital charge Q? At the center I am keeping a capital Q charge. What will be the force on that capital Q charge? Right? How to calculate that? So now the thing is that one charge is missing at the corner. Everywhere charges are there. Correct? Yes. How will you solve this? Huh? Hmm. Where? There is no charge here at this place. Everywhere else charge is there. So what we can do, what is the approach? Here we can use the first concept that, so where here charge is zero, right? Here charge is zero. So what you can do is you can write that there is a set of charge plus q and minus q. You can write here plus q and minus q. Yes, can we write here? Because if I write plus q and minus q, then what will happen? For example, let us leave for some time minus q. Then this effect of plus q everywhere now become plus q, right? Right? If you just ignore right now minus q, if you ignore, that means everywhere plus q will, those effect will get cancelled. That means now you can convert this system. This system can be just converted as a charge of minus q kept at that point n. Another point, you can consider the charge of minus q, that's all. And this is only for calculation of the at the center. So if you want to do calculation at the center, which is the most symmetric point, so at the center you have kept a charge of plus q. Now for that charge which is kept at the center, you can consider this entire system to be just made up of a single charge minus q kept at that corner where charge was missing. Are you clear? Yeah. Yeah, these charges got cancelled because this plus, all these plus charges has no effect at this place. But but because we are here, it is zero charge. This zero charge we can write as plus q minus q. If you write it like that, then this plus q will this plus q and all this plus q will contribute zero effect here. But then this minus q which you have written, this minus q is extra charge which you have written, which will be creating effect there. Are you understanding? What? No, that plus q is making effect, but that plus q combined with all other remaining n minus 1 plus q's, all those effects get cancelled. Understood? Yeah, that is what you have to understand. So that is why we have written zero charges plus minus, so that this plus will become symmetric and its effect will get cancelled. So this system can be now written as just minus q here, and this is a very good idea. Are you understanding? And so what will happen is that this charge at the center will just get, let us say this is positive charge, it will just get attracted towards that point where charge is missing. Understood? Hmm. Ah. Hmm. Where we can draw hexagon? No, okay, yes, if you are saying that you can draw hexagon, let us say six sides you are taking. Okay, hexagon you are saying, so take six sides like this. Okay, then let us take plus q plus q plus q plus q plus q, and at the center let us take capital Q. Correct? Ah. Then what you want? Yeah, that is right. That is right. See, here you can say that this exactly opposite effect will cancel out. Yeah, this effect will cancel out. You can also say that this effect will cancel out, right? And then this is the only effect, so it will create. This is another way of saying. But suppose if it is a, let us say that it is a pentagon. Let us say it is a pentagon. Pentagon, if you take like this, pentagon if you take, then plus q plus q plus q plus q, and at the center capital. Now how will you say, because this there is no opposite charge opposite of this plus q. Here it was opposite, so you can say okay, this interaction cancel, this is opposite cancel. But when pentagon is coming opposite, that means you have to do vector calculation there, right? Vector calculation you have to do. So that is how we are using this idea, that if I create a charge of plus q and minus q here, so the effect of these plus q's, this plus q effect, all these plus q effect at the center will become nil. So now you can only consider this minus q interacting with this q. Clear? That is what this concept is used. And actually your idea is correct, but the thing is that here vector is very looking very simple, so it is getting cancelled, but here it is not looking simple, but even that vector result will give the same concept. Okay, right, so this is an important property of cancellation. Then let us go to the next. But when you will be studying potential and potential energy, there also some cancellation property will come, that we'll see afterwards. Okay, right, then next, so this is property of charge. This is the fifth property. Sixth property, let us take property number 6. Property number 6, charge. Charge uh, charge is relativistically invariant. Invariant. Relativistically invariant means what? Relativistically invariant means, if like mass, if you consider relativistic physics you have to apply. So if you take mass and if you move it with a very high speed near to speed of light, then mass changes with speed. Okay, so here you note that mass, according to Einstein Einstein's theory of relativity, mass changes with speed. Mass changes with speed. M is equal to m naught root under 1 minus v by c whole square. Here m naught is called rest mass. Rest mass. V is the speed of the body and c is the speed of light. Have you seen this formula before? Yes. Might be you have seen in units dimension chapter, they give this formula to check the units or dimensions of that. Okay, so if a body is going with very high speed, let us say if a body attains the speed of light, then 1 minus 1, it will become 1, 0 it will become in denominator, mass will become infinity. That means it cannot now it cannot accelerate further. Suppose if you apply a force on a body, ideally means what? If you apply a force, that means constant force, let us say, that means it will be having a constant acceleration. Constant acceleration means what? Its speed will keep on increasing. Let us say it becomes speed of light. After that it will not increase because mass itself will become infinity. Mass become infinity means it cannot accelerate further. The force will have no effect after that. Okay, so this theory or this idea is not applicable for charges. Invariant means it is not going to change. Variant means change. So relativistically invariant means with the speed it will not change. Let us say particle has some charge, and even though it is going with a speed of light, its charge will remain same as it is. It will not change. Okay, sometimes they may ask this question, but generally it is not used. Then next, property number 7. Now property number 7 is also very interesting property. Charges create field and the field applies forces on other charges. Suppose if you take, for example, a charge at rest, this charge q. This charge q is at rest, let us say, because electrostatics we are studying. So what is the idea of field. Field means what? Field means the space around the charge where it can produce electric effect or magnetic effect if it is moving. But here we are studying electrostatics, means the charges are not moving, so it will only produce electric effect or electric forces. Okay, so how does this charge will apply force on any other charge? So it, because it is not in contact, right? Because let us say if you bring any other charges, let us call this charge as capital Q. Capital Q, sometime it is called as source charge. Source charge. And if you bring any small charge, small q, at some distance away from it, let us say r is the distance. Now this charge will experience force because of this capital Q. So how is this capital Q interacting with that small q? It has not even touched it. Just like in gravitation, bodies can apply force without touching it. How? Is it a magic? No, it is not a magic. Okay, because this source charge has already created something around it, and when any charge is coming in that environment, it will experience the force. Okay, so because this charge you are placing it this point, there is already field created due to this charge. Okay, and that field will apply force on this charge. This is how electric forces or electric field work. Okay, and how do we define the field? Field is defined as field is defined as the force per unit charge. Force per unit charge, and here we apply condition that limit q tends to 0. Why should we apply this condition? Because while you are trying to calculate the field or field intensity, this is also called field intensity, where while you are calculating it, at that point this charge may also attract or repel it, so this charge may get disturbed. So source charge should not get disturbed while you are trying to calculate the field, right? So that is why this charge you have to take as very very small, and generally this charge is taken as positive charge. So this is called test charge. This charge is called test charge, and the test charge is taken generally as positive, and it is taken as very very small, very very small. That is why this condition limit q tends to 0 is there. Clear? This is the idea behind this. Yes. Okay, this is there. And now very important concept which is mentioned also in NCERT, but generally it is not clearly understood at this point, because in NCERT they have mentioned that, let us say if you move this charge, then what will happen? Let us say you move this charge, then how the force will change here, because right now this charge is creating a field and that field is applying force on this charge. But if you move this charge, then what will happen to the field present at that location? The field will also change. Okay, suppose you move this charge, then because the source charge itself has moved, the field created due to source charge will also change. Okay, but the change of the field will happen instantaneously, and it will take very very less time. Okay, the change of field at that point will take very very less time. Why it takes less time? Because the field behaves like a wave. The field, the electric field, which is nothing but the space around it, that wave is starting moving with the speed of light. Okay, but this thing is just given to give you idea that electromagnetic wave is developed there, and electromagnetic wave travels with the speed of light. So this point let us note here. Right now we'll just try to first write this point. So if the source charge, if the source charge capital Q moves, then the field at the test charge, field at the test charge changes instantaneously instantaneously with a very with a very small time gap because the electric field because the electric field due to the source charge due to the source charge propagates propagates with the speed of light with the speed of light. So if you are moving the source charge, the field will also move, but field will move with the speed of light because field is something which is like a electromagnetic wave, and the effect of change in field will be quickly seen at the source at the test charge. Okay, so force will change means the magnitude of force can also change and the direction of force can also change, but the change will happen very fast because in very less time it will happen because the electric field travels with the speed of light. Are you clear about this? You will read this paragraph now in the NCRT, and then there will be many more points will come. But right now, this thing will be coming in electromagnetic waves chapter. Okay, and this year NTA in J main they have asked a question which nobody has expected, and everybody is complaining how it is possible this question. Nobody knew how to solve it because they never asked such type of question, and this it is based on the same idea that how electric field propagates with the speed of light. Although they have studied this concept in electromagnetic wave, but when actually the question came uh, about calculation of some current, it is very difficult. We did not know because in current electricity also we did not study this. So NCRT is a very important book because you have to study deeply and they can ask questions from any paragraph. Okay? Not only for NEET, it is J or it is also advanced book. Okay? Right, so these are about the properties of charges. Clear? Any doubt in this? Hmm. Now let us move then next. Next we will move about forces. Forces. Electrostatic forces. Electrostatic force. So for this we have to study Coulomb's law. Coulomb's law. What is Coulomb law? Coulomb law gives the equation to calculate electrostatic force between 2 point charges. Okay, so this gives an equation. It gives an equation to calculate the electrostatic force between 2 point charges. And what is meant by point charges? Point charges very important. You have to understand point charges. Just like in gravitation, you have studied point masses. Same way, point charges. So point charges means suppose this is a body. It may have some dimensions. Let us say it has a size or diameter here. Similarly, another body is there. But these two bodies are very far away from each other. The distance between these two bodies, this distance r, is much larger than a. So these two bodies can be treated as point bodies. Now here this is a very important thing, that point charge does not mean that the body is a point, charge is a point. So point charge means the body is like a point. The shape of the body can be anything, but the size of the body is negligible, as compared to distance between the bodies. For example, let's take example of stars. In the sky in the night you see stars are twinkling, it looks like just a point, but actually the stars are so big, we are nothing in front of the stars, right? It is so big, but why it is looking like a small point? Because the distance is so far, very very far away it is. That is the reason. So you can take the same concept, the charges, point charges means the charges are charges can be any value, it can be very high value of charge, but the bodies are like point objects, okay, like a very very small. Actually it is not possible ideally that body can be a point, it is not possible. Even if you see electron can be considered as a point because its size is very very small, but some size is there, right? Why we are saying electron is very very small? Because as compared to atom, as compared to everything else, it is very very small, so we say it is like a point. So point charge means that only, but the value of charge can be anything, it can be 10 coulomb, million coulomb, whatever it is. Then you can write the force between these two charges, and we can represent this point charges as like a point, we can represent like this. We can represent, let us say that it has charge q1 and this point has charge q2, and this is the distance r. So there will be force of interaction between them, and this force is proportional to the product of charges, and it is proportional to the square of distance between them. And when you remove the proportionality, you will get a constant of proportionality. Hmm. Yes, yes, Kevin. It is not. It is the magnitude of charge. Sorry, magnitude of force. The magnitude of force is proportional to the product of charges and inversely proportional to the square of distance. Huh? This is product of charges. See here, when you're talking about this magnitude, right? When you're talking about the magnitude of force, then this is also magnitude only. Correct? When you take, let us say Q1 is positive and Q2 is negative. So you are taking the product of magnitude only, or you are taking product and then taking magnitude. Understood? So it is not that we are saying, suppose if you do not take magnitude in right side if you take with proper sign, if you take proper sign, then here also force will get some sign. Suppose you take plus plus, plus into plus will give plus, minus into minus will give plus, plus into minus will give minus, minus into plus will give minus. So from there you can understand something, that if force comes positive, that means repulsion, and if force comes negative, that means attraction. Clear? Are you getting that? So do not worry about this sign, we are just taking the magnitudes of that product. It's the magnitude of product, or it is the product of magnitude, that also you can write. So it is the product of charges, means whenever we are telling this side magnitude of force, means this side also magnitude, okay, that we can understand. So it is the product of charges. So magnitude of force is proportional to the product of these charges, magnitude of charges, and inversely proportional to square of distance. When you remove this, there will be some constant will come, and this constant will be q1 q2 by r square. Okay, q1 q2 by r square. Now suppose if I write just the electrostatic force, suppose I write in this statement, because how you present the statement, that is important. If you are including the correct signs with the statement, then it's okay, then you don't have to write magnitude. Suppose if I say that force is proportional to the product of charges and inversely proportional to square of distance between them, and if the force is negative, then it is attraction, and if the force is positive, then it is repulsion, then your statement is correct. Then you don't have to extra explain about negative positive thing, right? That negative positive thing will automatically can be understood, because similar charges repel and opposite charges attract. Correct? Yes. So we don't have to explain that, but you look in the statement given by NCRT what it is giving. Maybe they are writing that magnitude, otherwise they will give that sign plus minus. Okay. Now here important point to note is that what is this small k? What is this small k? And also note that we are writing this in vacuum. In vacuum. In vacuum you are writing. What about the medium if you write? Okay, and note that this small k is 1 by 4 pi epsilon naught, and its value is 9 into 10 to the power 9 Newton meter square per Coulomb square. Okay, and what is this epsilon naught? Epsilon naught is called electrical permittivity of vacuum or free space. I should use headphones, that will be better, because I am not able to hear when you are speaking better. I will try headphone or some earphone next class. Okay. Okay, so in vacuum, when we are taking in vacuum, so we can write the force like this, and here this epsilon naught means it is the property of the vacuum. But what will happen if you take a medium? If you take the medium, then what will happen? Let us think of writing this force in medium. So this force in medium will be, this k I will write as 1 by 4 pi epsilon. Now instead of epsilon naught, I will write as epsilon. And other things will be same, q1 q2 by r square. Okay, so this is the force in medium. In medium, then what is this epsilon here? Epsilon is what? Epsilon is electrical permittivity in medium. In the medium, whichever medium you are taking, in that medium it is electrical permittivity. Okay, what is electrical permittivity? Basically, just like any substance has property like electrical property, mechanical property, physical property, thermal property, chemical property, all these properties are there. Similarly, this is an electrical property of the medium, and if it is vacuum, it is called epsilon naught. If it is not vacuum, it is simply called epsilon. Okay, but this epsilon and epsilon naught can also be related. They can also be related. How? Just like we have a term called relative density. What is relative density? Yes, relative to water, it is the ratio of density of a substance by density of water. With respect to water, you are comparing. Similarly, there is a term called relative permittivity. Relative electrical permittivity, okay, which is called epsilon r, or sometime it is called as k. K symbol is sometimes used for dielectric constant, which is the same thing. Dielectric constant, dielectric constant is same as relative electrical permittivity. So this relative electrical permittivity epsilon r can be written as epsilon of the medium by epsilon of vacuum. So with respect to vacuum, we are comparing that. Okay, so this you can write as k also. So now if I substitute this in this formula, so epsilon will become what? From here you cross multiply, epsilon will become k times epsilon naught. Then we can substitute here. Okay, so force in the medium, force in the medium will be 1 by 4 pi epsilon K times or epsilon naught times K Q1 Q2 by R square. Now, if I club 1 by 4 pi epsilon naught R square Q1 Q2, that is the force in the vacuum, right? So, this is the force in vacuum, and capital K I will leave it. So, force in vacuum divided by capital K, correct? So, this is how we can relate force in medium and force in vacuum. So, force in medium is equal to force in vacuum divided by the medium property, which is called dielectric constant or relative electrical permittivity. Are you clear about this? Now we will be winding just few minutes. One important point to note here, that the value of K will lie between uh, 1 and infinity. So K is 1 for vacuum, capital K is 1 for vacuum, and K is infinity for metals, metal or conductor, metal or conductor. That means inside the metal or inside the conductor, even if you keep some charges, there won't be any force between them. Why? Because K is infinity. If K is infinity, then anything divided by infinity will become 0. So there will be no force inside the conductor or metal. Okay. So this is all about, and here also you note the value of epsilon naught. Epsilon naught value comes as 8.85 into 10 to the power minus 12 um, Coulomb square per Newton meter square. Okay. Now, using all this what we have discussed, you can start doing calculations on the forces. Okay. So simple calculation will be there. Very simple calculation you start with. Suppose for example, if you take 1 coulomb charge plus 1 coulomb and another plus 1 coulomb charge at 2 points and separated by 1 meter distance in vacuum, what will be the force of electrostatic force of repulsion? So we can calculate the force. We know that repulsion will happen because charges are similar, but the magnitude we can calculate easily. 1 by 4 pi, that means 9 into 10 to the power 9. If you want, you write it this first, small k q1 q2 by r square. This k value is 9 into 10 to the power 9, and these charges are 1 into 1 divided by distance is also 1 square. So this force is very high. You can see that it is such a high force. 9 into 10 to the power 9 Newton is tremendously high force, correct? Okay, so now you can work out problems like this. Start solving basic question, start refer to NCERT, first go through solve problem and then start solving some questions from exercise. I will be also sending worksheet, then you will be starting working out. Okay, fine. Okay, anything, any doubts you have? Okay, fine, then we'll see next class. Bye bye. Yeah, thank you.